I guess I'll go ahead and introduce our state paleontologist, Jim Kirkland. This is probably his 22nd UFOP talk. Maybe not just this chapter, but between all of the chapters, he's given quite a few. Does anyone in here not know who Jim Kirkland is? Okay, that's what I figured. Jim, like all the other UGS paleontologists, was born and raised in Massachusetts, as was Martha and as was I. He was born in a marsh that they drained and it became a field, so they named it Marshfield. So that's where Jim left Boston area to come to college out in the West, and he's never gone back. So about 50 years ago, he graduated from the New Mexico School of Mines in Socorro, New Mexico, and he's been a Colorado Plateau person ever since then. And did his PhD, or he did his master's then at University of Northern Arizona. Then he went to CU Boulder, do his PhD. He was a Mancos invertebrate guy, so really steeped in geology and paleontology. But his first love since he was about 5 has been dinosaurs. So he eventually got away from the invertebrates, did dinosaurs, was at Dinosaur Journey in Western Colorado for many years, started their program there, built that museum. And then he's been state paleontologist here for 27 years. So he was just a newbie when I came on to work with him. So published on tons of geology, has named 27 dinosaurs or something at this point, with many more to go, but pretty much a legend, also a sweetheart, and a guy who knows a lot and is really happy to tell you about it. So I always say if I could remember everything Jim told me about geology and paleontology, I would be really smart. So without further ado, we're going to bring up Jim Kirkland to tell you what his most recent project is. He's always got a new project, and this is the most recent one, so thanks.
Thanks, Tom. I see the red title up there, Dino-Decimation. Basically that came up, I gave this talk in Moab about a month ago, and a shorter version I presented at the 12th International Conference on the Cretaceous in Germany about a month ago as well. But that, they give you 12 minutes, and as you'll see here, it's a lot to cover in 12 minutes without much question. But, I've been out here working the Cedar Mountain Formation since 1989. 1990 really started getting into it in a serious sort of way. And people say, oh, you collect all these fossils, you're just collecting marbles. Well, as you get enough marbles, you can do something with them. You start putting them together and building a pyramid and building other things. But we've been collecting so much data that we are now in a position where we can really start saying some important things about the history of Utah that we didn't have a clue about. And the thing I've been working on for the last year now is getting the data together on the Jurassic-Cretaceous boundary. And just repeat what I'm going to say over and over in this talk. We have the best record of this sequence in the world. And I've just submitted my stuff to some colleagues in China, working with a number of my colleagues in Britain, Mike Benton, and a few others, putting together a big database for the Jurassic-Cretaceous in the Northern Hemisphere to show how, this also is happening in China and in Europe. This is not just Utah, but we have the best record. So why don't I go on, see the mouse. Oh, there's the arrow. There's the Utahraptor block. We're going to talk about that, but we will mention the Weissert OEE, which is an international correlation point. Okay, so let's go forward. Yeah. So basically, you've seen this more than once. You've come to my talks. We have the best record of the Mesozoic terrestrial sequences anywhere in the world. And we've really figured this out, started pulling this stuff together before I got this job. It's what helped get me this job to begin with, things like Utahraptor. But if you look at what we've come up with over the last, now let's say 26 years, We had 22 dinosaurs known in Utah with names on them. 22, almost all from the Upper Jurassic Morrison Formation, which we're clearly famous for. But look where we're at now. And there's bunches of institutions that are sitting on new dinosaurs that haven't been named yet. There is bunches of things in the pipeline coming along. One was just named last week. They renamed Alamosaurus at the very top, that sauropod, U-Titan. But the way it was done, a number of us are not thrilled with. Now, I'm going to start with the end of the Cretaceous. Everybody's familiar with what killed all the dinosaurs. But the thing to keep in mind with these extinctions, dinosaurs are players. They're the megafauna, the thing we think about. But they weren't the only thing that went extinct at the end of the Cretaceous. And if you look at this chart, the end of the, it's one of the big five. I don't see this mouse. I don't see the arrow on here. Oh, that's interesting. So I have to look over here. Okay, that's harder to do. But basically, it's one of the big five extinctions, number 5, the end of the Cretaceous. And we lose dinosaurs and marine reptiles and ammonites and the reef-building rudisted bivalves, all kinds of plankton, as I'll talk about in a second. But I got this question mark here between 4 and 5, showing there is a kick at the end of the Jurassic. And generally, there's not a good record there. So, it shows a kick at all is of significance. One of the things people don't think about, the extinction, they always think dinosaurs, so throw up a few groups. There was a mass extinction among bony fish and sharks and rays. So if you look at this chart here is this thing. See, the rays undergo a gigantic extinction. Whole families go out at the end of the Cretaceous. We don't think about them all that much, but look at even the sharks. Everybody says, oh, sharks have been around forever. They underwent a massive extinction. The modern shark assemblages are really a Cenozoic group, except for the big lamnids. But overall, we don't have much of the Mesozoic and none of the Paleozoic shark group surviving. And look at bony fish. Look at all the different bony fish that go out at the end of the Cretaceous. And are replaced, often with a gap, by other fishes as these fish radiated to fill these niches. A massive extinction. We're not talking about half of the mammal taxa went extinct. 2/3 of all marsupial groups went extinct. People just, mammals lived. Well, more than half didn't. And this is at the family level. Oops. Okay, that's working that way. Plankton, this is just a chart showing the nanoplankton, the tiny single-celled plankton, the base of the food chain in the oceans. Pretty critical to the health of our planet, the oxygen CO2 budget of our planet. And you look at the end of the Cretaceous, we lost almost all the nanophytoplankton. This is the stuff that's consuming CO2, fixing it, and then goes to the ocean floor within copepod fecal pellets. But it gets there anyway. But you look even above the Cretaceous, you say, you get some stuff. Everyone realizes that's all reworked. You get burrowing organisms, they just churn this stuff up. And this stuff is tiny, this nanoplankton. But look at how these groups of nanoplankton re-radiated. People I always thought when I first learned about this, just this happening could explain the total extinction, because what it would have done to the atmosphere, with the CO2 budget and things of that sort. This would have been a big deal. It's all part of that same event. But what was the cause? Why did this thing happen? And as I said, there were a lot of things that are coming up, people discussing this. One of the things I liked, I thought it was a great story back in the 80s, was the Arctic Ocean opened up and flooded, became very fresh for a while, the upper part of the Arctic, and it flooded into the world's oceans, and that's what killed the plankton. It was this freshwater flush. And that was the chain reaction that started and killed everything else. Well, we know that's not true, but it was a reasonable theory at the time among many, supernovae in the immediate, area in the galaxy, So radiation influx to the planet. But Walter Alvarez, the young guy in the blue shirt, chatting with his dad. He was doing geology in the Mediterranean region. His dad came to visit him in Italy, working on the marine sequences there, crossing Cretaceous-Paleogene boundary. And he said, Dad, look at this. Right here, I put my finger right here. This is the boundary between the Cretaceous and the Tertiary. This is the extinction event in the plankton, right here, this line, the little black shale going through there. And his dad said, I wonder if that represents a gap in time. You know, if it was a period where there wasn't much deposition, and that if there was, you know, if we look at things like, look at iridium in these rocks, we should see the iridium concentration going up some. Because iridium comes in, as far as we can tell, at a constant rate from extraterrestrial sources throughout time. So it's a steady state thing coming into the atmosphere. So if there's a delay in these marine rocks or slow down deposition, we're going to see that increase relative to the thickness of the rock. So they said, okay, let's microsample and look for iridium. Whoops. Oh, come on. I cannot see this. It's not on this screen. How do I go back? How do I get rid of that? I can't see anything from this angle. Right there? Oops, no, I didn't want to. I wanted next, sorry. Okay, I can go next. Oh, don't do that every time I press the button now. Okay, I'm going to try to do it this way again. Okay, so anyway, they sample for iridium through this sequence. And basically, the spike of iridium was hugely bigger than could be explained by a change in deposition rate. You know, and iridium is extraordinarily rare on the Earth's surface. It's really the source we get for what we see on the Earth's surface is extraterrestrial. So they proposed that this must be a fallout blanket from a major asteroid or comet impact somewhere on the planet. Don't know where, but somewhere there was an asteroid impact that came in and collided with the Earth, and that's what killed the dinosaurs. And of course, paleontologists were outraged. You know, like the world, it's gradualist. Everything goes slowly and majestically through time. And had a catastrophic event like that, not a chance that this could be true. And these guys this is a geophysicist and a physicist. Even though he won a Nobel Prize, who cares? He's not a regular geologist. So what is he doing telling us what's happening? So there was a lot of outrage in the profession. Paleontologists were really upset. But they had a conference a couple years later in Snowbird, Utah. It brought people in from all over the world to talk about the Cretaceous-Paleogene boundary, talk about this boundary in depth. And over that next decade, after they proposed this, there were 2,000 published papers. You know when you've thrown something out that's interesting to people, when you get 2,000 published papers in 10 years on the topic. So there's a lot going on. That Snowbird conference didn't come up with any real answers, but certainly got the topic discussed. Well, in 86, November 86, I was brought down to the Brazos River by my major professor that I was working on my PhD with, Earl Kaufman, the University of Colorado Cretaceous Attack Team captain. And he was hired by an NSF group, largely of Europeans, but Tora Hansen from the University of Washington was leading our group down there to look at that sequence across the extinction boundary along the Brazos River. And that little bench there with the arrow coming down toward the Brazos River, just here where it is on the map, that's a sand unit. And it's about 30, 40 centimeters thick, a little over a foot thick, a pretty much clean sand with big burrows in it. And it sits above like pure clay full of fossils below it. And basically their scenario of what was going on there, that was a big hurricane storm bed. You know, it reworked the sediment, and a large hurricane had come across the Gulf at that time and gave us a little bit of a gap. A tor was a nanoplankton biostratigrapher. He thought, well, we're missing about a half a nanosone here. So not a lot of time. This is a pretty complete sequence, but we're missing a little time. And a storm bed would explain why we'd missed that little bit of time. And I'd been working in the Western Interior, my PhD, Wamako Shale, looking at the regressive sequences. And when you look at storm beds or tempestites, you see bunches of them. If you're going to have a hurricane, 100 years later, you're going to have another one. Hurricanes repeat themselves. So you don't get one giant hurricane and nothing above and below it. A single bed, nothing above and below it. Pure clay above, pure clay below with fossils. So it didn't fit storm bed scenario for me at all. And I made a suggestion out here that turned out to be probably correct. I proposed that this was a tidal wave deposit. I'm the first one ever to propose this. And I proposed it was a tidal wave sequence, and that basically the sequence you see here, if you go through, from the bottom to the top, basically we have a healthy Cretaceous marine fauna. I spent 2 months going through all the fossils we collected. We collected every 5 centimeters, big sacks full of the shale. And I identified and collected the fossils and identified them. It took me months going through with a needle and identifying every single mollusk that I came across in there, shark tooth, whatever. And no change through that whole sequence. And then we get up to the base, and there's this gravelly layer. Might be easy if I point. Right in here below the sand, you see carbonate nodules, all this green and iron stain. That's from glauconite, this green mineral that often forms in foraminiferal plankton tests. Angular chunks of claystone, just this rubble bit full of shark teeth, almost a shark tooth gravel. I mean, I was screen washing some of this, and I was like amazed at the amount of shark teeth. And basically, when I was looking at that bed, I said, okay, this is from the erosion of the tsunami over the continental shelf. And it's just wearing it down, and the coarse stuff's being left behind. Also, I was looking, and we have these angular clay clumps that are rubbery. How'd this happen? Couldn't figure that one out. I just, no clue. And then above this, we see a sand. The sand is when the wave went up on the Gulf Coast. When it came back, it pulled all the beaches off and spread the sand out over the continental shelf, over the whole shelf region. We're 50 miles probably from the shoreline at this point, when we're looking at this. So it's a big event. And then there are burrows and whatnot in that. And then we go back up into the marine rocks above it, and we see a very depauperate fauna. Not many taxa. Pleurocardia, which is like the marker for the base of the tertiary Texas, occurs in there, but not much. Very low diversity population of invertebrates. So if you look at this scenario, right before I went to teach in Nebraska, Earl had me in his office, and he said, Jim, lay out what you said out in the field, what you think is the scenario. And I laid out this complete scenario, as you see in black, for him. I said, I just don't understand those angular clay clasts. Maybe there are submarine channels and the sides of them ripped off, to give us these things. And they published about a year and a half later, after I went to Nebraska to teach at the University of Nebraska, a paper in Science. And that totally used my scenario, point by point by point, but they did figure out where the clay class came from. That tidal wave hit the edge of the continental shelf like it was a seawall, and just ripped the whole edge of the continental shelf up and scattered it out over the continental shelf itself. But that was the only thing I missed. And we all missed the volcanic ash that really accurately dates the boundary that was only a couple of feet below the boundary itself. And I can't believe we missed it, because we were dating ashes regularly in the Manco Shale at the time. But anyway, so I was a little sad because I never got even an acknowledgement. This knee is called Brazos because I hyperextended it carrying samples out of there. So I remember it real well. Whenever this knee hurts, okay, that project. But Earl was hired as a hired gun. I was his hired gun. So I understand the people in charge. You see, he's not the first author. He's the last author. They didn't want his student, to be on the paper. This happens all the time. But the paper came out in 1988. Following year, this student, Alan Hildebrand, who was a grad student at the University of Arizona, read the paper, and his advisor said, this would be a great project. Let's go to the Caribbean and see if we can find more evidence of a tidal wave down there. And, yeah. And why Earl and his team, Tor Hansen and those guys, didn't follow up, I'll never know, because that, to me, was seriously low-hanging fruit. But they didn't, but Alan Hildebrand did. And he went down there, and on Haiti, he found 0.5 meter of tektites. Does everyone know what a tektite is? Little molten glass beads from an asteroid impact, and very collectible. 0.5 meter of tektites on Haiti and other tektite layers elsewhere. But the fallout blanket from this impact. He thought it was a structure he saw in Colombia was the impact site. So he didn't have the right site, but it was in the neighborhood of where it really is. But, he was wrong in where the site was. However, these guys saw the paper he published and gave him a call and said, we think we might have an impact site you'd be interested in. And there's core in New Orleans from our oil exploration work that drills right through the stuff. And I think we can find that core and we can look at it, see what you think. And that's how they discovered Chicxulub. And these guys first identified this as an asteroid impact site on the Yucatan in 1978. Look at the timing of this. 78. And they didn't get permission. They worked for Pemex, petroleum oil company in Mexico. So they weren't given permission to write about this. And they finally got permission a couple of years later, and they presented it at Society of Exploration Geophysicists meeting in 1981, which was happening simultaneous to the meeting in Snowbird, Utah, where everybody with any interest in this was at that meeting. So they gave this talk, and everyone just snored through it. They're all geophysicists, exploration, oil and gas. We don't care about this. So no one did anything. But as soon as they told Alan about this, got him to New Orleans, looked at the data, they published the next year, 1991, 3 years after Earl and that paper came out, and identified Chicxulub. And there's Walter Alvarez with them, years later, talking about that discovery. But that chain of events is like, man, I lit the fuse and I got nothing out of it for this. But fortunately, we've got some other things to talk about. Here's the asteroid impact, once again, gigantic thing, as I've labeled. And this is not my work, but the wave hitting the continental shelf like a seawall, bottom from the top, image down there. But this is a big event. And what's incredible, when you look at it, they figure it was 10 kilometers across. So they had 7.5 miles in diameter, plowing into the earth, making a crater, 130 miles across, 30 miles deep. Gigantic hole. Well, when it hit, basically, this, the crater diagram, it evaporated. It hit a barrier reef. Think of the Great Barrier Reef in Australia. 100 miles of a Great Barrier Reef system evaporated into the atmosphere. Behind it, there are all these sulfates. That evaporated into the atmosphere. Water evaporated into the atmosphere. You couldn't think of a worse place to drop an asteroid to affect the planet's atmosphere and biota as right then. And basically that extinction, clearly, it killed mollusks off. It killed off, an incredible suite of animals. Plants, 80% of the macrofossil plants went out. People say, oh, no, it's just the dinosaurs. No, it isn't. It's everything. Got hammered. And the work the Denver Museum's been doing down south of Denver, they've been able to show, because they have a record right from the iridium layer up with fossil mammals that they're now filling in, and they can show how quickly the mammals started getting bigger, the ones that did survive, and started becoming substantial animals within the ecosystem. But the recovery is slow, and it took, millions of years. and probably 10 million years before you got an animal weighed a ton anywhere in the world. Now, let's go to the big one, the important one, end of the Jurassic. Utah's famous for its Morrison faunas, incredibly diverse big carnosaurs, diverse sauropods. Climatically, it was temperate, seasonal, monsoonal climate, but net evaporation. We have carbonate, salts in the soils, calcitic soils there. But one of the things we've been doing is dating these rocks, and the very end of the Jurassic does not seem to be present on the Colorado Plateau. So where are North America's latest Jurassic dinosaurs? We don't seem to have it. We have a little bit of Tithonian in the last stage, but don't have much, apparently. There doesn't seem to be any in Wyoming, but the Denver Basin, Cimarron County, Oklahoma on the east side, Garden Park, Pueblo area on the west side, they have a fauna that at the top of the Morrison that includes giant dinosaurs. Thing we used to call Saurophaganax, now it's being called Allosaurus anax, but it's a giant allosaur. We have a giant 90-foot Apatosaurus. There's a Diplodocene that is ridiculously big from over in Garden Park. Camarasaurus grandis, which is the biggest of the Camarasaurs, is at that level. So that might be this Tithonian. There's no good dates from those rocks, so we can't prove it. But it's a different fauna than we see on the Colorado Plateau, and it's much bigger stuff. So if you look at Cope's rule, things tend to get bigger through time if everything is going well. And apparently things were going well. We do get the boundary in Europe, Iberian Peninsula, the Gobi of Europe. It's just really getting into it now. Portugal, I've been to both of these sites and done work with these guys. Got a student in Portugal just defended on an ankylosaur from the Tithonian over there. But the fauna is very much a Morrison kind of dinosaur fauna. And it's both in eastern Spain and in Portugal along the coast. Here's just some of the charts showing, yes, there are dinosaurs going right up to the boundary. And they've got little marine tongues here and there that they can date with marine fossils and tie into the global time scale. So they really know that this does go to the end of the Jurassic, which is real exciting. So the Morrison-style faunas, the Morrison has got an incredibly diverse fauna, more than 100 taxa, like 30, 40 kinds of plants. Dozens of mammals are known from it. But we're going to really focus, here on the dinosaurs, because the lower Cretaceous in Utah has been stingy with our little vertebrates still. We'll get them, but it's been stingy. We're well down on that learning curve. If you look at what the Morrison fauna is like, a diversity of big sauropods, diplodocids, brachiosaurs, camarasaurs, gigantic, diversity. There's like 20 kinds of sauropods known in the Morrison. Any decent site has 4 to 5 different taxa living together. Niche for some feeding high, some feeding low, but in the same site, any decent site's got several kinds that were living together. And then we got a variety of big meat-eating dinosaurs, completely unlike what we see in the Cretaceous. Saurophaganax at the end is a huge allosaur. Torvosaurus, big megalosaur. Of course, Allosaurus, Ceratosaurus, the last of its line. Stoxosaurus, Marchosaurus, probably related to Torvosaurus. It's a megalosaur grade animal. And then Stoxosaur, which is a tyrannosauroid. All these animals are present in the fauna. Diversity is now thought to be 4 kinds of stegosaurs in the Morrison. Of course, Stegosaurus being the most common. There's 2 kinds of ankylosaurs. I got a paper just submitted, and it just came back from review, got good reviews on the ankylosaurs. There's 2 kinds living together in the Morrison, and then a variety of bipedal plant eaters, small to large, and a couple of small meat eaters, including one feathered animal that may have ties to the origin of birds. But there's incredible diverse dinosaur fauna. This is from 2024. I'm really happy because they do reference my stuff from the same year, so they're very up on what I've been doing. But Bill Mannion did a paper on the distribution of Mesozoic dinosaurs globally, and shows, yes, there is a big change at the end of the Jurassic. But exactly what's going on, it's hard to tell because these are very rough numbers. The dates are very fuzzy in many of the sites they're looking at. But Utah, we have the best early Jurassic sequence anywhere in the world. And I haven't talked to a geologist that has a clue what we're doing that doesn't agree with me on this. I mean, I've toured the Chinese around Utah twice, the Chinese Geologic Survey and the Academy of Sciences. They agree. We are the keystone for the early Jurassic globally, particularly in the Northern Hemisphere where they're interested. But you see this, wealth of things. We only knew of a couple animals here before we found Utahraptor. And one of the things that had been described from it, we rediscovered the site. It's actually from the Morrison and not from the Cedar Mountain Formation. But we just thought, this is just Aptian Albion, nothing interesting going on. We now realize it's a complex unit, and it spans 45 million years of Earth history. That's more than two-thirds of the age of mammals. There's a story there, and we're just starting to get into it. And the rocks we're going to really be talking about for the most part are the yellow cat rocks and the poison strip. We're going to bring those up repeatedly as we go through this talk. So just the yellow cat, there's a lower part, that's the basal zone, the Berriasian, and the upper yellow cat, Valanginian. Of course, the Morrison is Kimmeridgian, Tithonian boundary in this area. The geologic setting, why do we have this incredible record? If you go anywhere along the Rocky Mountain escarpment, from Mexico all the way up into Canada, we see about a 20 to 25 million year gap between the top of the Jurassic strata and the beginning of Cretaceous deposition, which is generally in the Aptian, the middle part of the early Cretaceous. And that ties to a return to mountain building activity. And working with colleagues at the U.S. Geologic Survey, they have pointed out that there is no mountain building happening during Morrison or early Cedar Mountain deposition. There's a quiescent interval. Before, in the middle Jurassic, you did the Elko-orogeny, and in the Aptian, you develop the severe orogeny, starts up and goes to near the end of the Cretaceous. But there's this period of quiescence, perhaps isostatic rebound. Maybe the mountains were lower and warm, moist air masses could come in. The gap is important because this is everywhere. This is why no one has ever been able to say anything about what happens at the end of the Jurassic. 20, 25 million years, I would say, the dinosaur civilization arose in the latest Jurassic and basal Cretaceous, and they killed off most of the life on the planet, and then erosion removed all signs of that civilization. If you got a 20, 25 million year gap, there's a lot of room. Humanity from the very beginning hasn't been around that long. That's a lot of time to be missing to try to say anything about anything. Now, why do we have a record here in eastern Utah that no one else has? It's salt tectonics. During the late Paleozoic, we developed a series of mountain ranges, the ancestral Rockies. The one we're interested in is the Uncompahgre uplift on the Utah-Colorado boundary. Big, huge. Think of the mountains there on the edge of Death Valley. Miles high. You develop this big basin in front of it. You pile up a big mountain range. The weight of the mountains give you a foreland basin in front of the mountains because it's just like an ice cube or the way icebergs work. You build something up and it's going to push down. So we end up with a basin on the steep side of these things, and that's the Paradox Basin. And because there was an ice age going on in the southern hemisphere during the Carboniferous, when the ice sheets would expand, sea level would drop, water spilling into this basin would evaporate, give us salt, the ice sheets would melt, sea level would come up, seawater would come in, and this happened repeatedly, over and over and over again, repeated expansions of this southern hemisphere ice cap. With this happening, we end up with like 3,000 feet of salt in the Paradox Basin. All the potash mines, economically very significant stuff. Been very well studied. There's books on it because of the economics regarding salt. But salt never turns into rock. And it's always mushy plastic. So you squeeze, miles of rock on top of it, squeeze it down. It moves like toothpaste. And if there's a fault, a weakness, it squirts up. It can squirt up into domes or into we get what we call salt walls in the Paradox Basin. And some of the big ones are, Fisher Valley, Castle Valley, big salt walls that come up. And there were actually salt glaciers like we have in Iran today, where the salt in the late Triassic came up in late Paleozoic and spilled out and flowed across the Earth's surface in Professor Valley. There's a couple of sites where that actually happens. It's happening today in Iran. You can look Landsat photos and look at it. It's really neat stuff. But because the salt's coming up, build these salt walls, the story's always been it stopped at the end of the Triassic. And nothing else happened. When we look at these rocks, we realize there's subsidence in the northern Paradox Basin in the late Cretaceous. We were working at arches. We have evidence for salt tectonics happening in the Pleistocene there, with volcanic ashes and folds that end up getting truncated. Salt always moves. It's never going to stop. If you squeeze it, it's going to move. Well, we think the salt was going south with additional sedimentation in the early Cretaceous along the direction of these salt walls that led to subsidence in the northern Paradox Basin, giving us this spectacular record. Once again, the rocks we're going to look at, we're focusing on the poison strip down, but this is the sequence of rocks. The first half of the Cedar Mountain Formation. So once again, lower Yellow Cat, upper Yellow Cat, and poison strip. We'll see that quite a bit. I think there should have been another picture back there. Nope. It's probably coming later. Anyway, the fossils in the Yellow Cat are incredible. Here's Poison Strip Road, 10 genototal-type dinosaurs. This is the greatest density of new dinosaurs. It's better than Dinosaur National Monument, better than Dinosaur Provincial Park, as good as the best stuff in China other than the bird beds, because they're all dinosaurs, so they don't count, they're little fuzzy. But this is one of the most fossil, dinosaur-rich areas anywhere in the world, and it's a free-for-all out there.
Jim?
Yeah.
Jim, what's the red line on that?
That's the road. That's the Yellow Cat Road. You go over by Green River, we have another area, Don's Ridge region. It's almost as good, and there'll be more. Los Angeles County Museum is out there working vigorously now, and I'm sure they'll end up naming a bunch of dinosaurs from those rocks out there. If you look at this map, here's the area. I've proposed for a while, as has other people. The Park Service, we've talked about it. It's not going to happen in my lifetime, but a future dinosaur dawn of the Cretaceous fossil beds national monument. But just the honey holes like Yellow Cat, Green River area, mustn't touch it, and Price River. So small areas, kind of like John Day fossil beds in Oregon. And this is the rock sequence, the Paradox Basin. Let's see if I move this. See, this is the Paradox Basin region. We have this lower Cedar Mountain area filling in that basin because of salt tectonics. We go west of the swell. It's a totally different section. But if we look at these areas, Yellow Cat, Green River, Price, and mustn't touch it, we end up with a complete sequence of 45 million years of Earth history full of fossils that were known nowhere else in North America. So very worth doing something with. The lower Yellow Cat, this is just some of the stuff. We've got a variety of armored dinosaurs, certainly at least two different kinds, a giant one and one a fair bit like Gastonia, a couple different kinds of iguanodonts, probably three kinds of iguanodonts, three kinds of therizinosaurs now. These are plant-eating animals, that originally were big meat-eating, they're small meat-eating, Maniraptorans, Falcarius, Gemini raptor, the new one from Doling's Bowl, it's a bigger one. Three different genera of therizinosaurs in the base of the Cretaceous. Of course, we have one kind of sauropod, Myotosaurus, which is a Toriosaur, a group of sauropods not known in North America at all until the base of the Cretaceous, but they were a dominant group in Europe during the Jurassic. So apparently they come in from Europe to replace things. Our Polycanthine ankylosaurs may be homegrown. They may have got them from us. Our camptosaurs, our iguanodonts might come out of Camptosaurus. But we lose almost all the theropods and the sauropods. They're being replaced by European taxa. Go a little bit higher, the upper yellow cat, we've got ornithomimids, ostrich mimic dinosaurs, but they still have teeth. There's some in slightly older rocks in France. So we know there's ties with Europe with this stuff. More ankylosaurs, polycanthines, more at least 3 kinds of iguanodonts. Of course, more dromaeosaurs. I didn't mention Yorgovutia, but of course we have Utahraptor at this level. We have some other small animals, but we also get a brachiosauroid Cedarosaurus. Moabosaurus is another turriosaur. But Cedarosaurus seems to be closer to Lusatitan from Portugal and not Brachiosaurus from North America. This is the European sauropod guys. I don't do sauropods, so sounds good to me. Got to believe the experts at some point. So we look at this. This is a little chart showing the section with some of the dromaeosaurs, Yorgovutia, Utahraptor, the new relative of Utahraptor from Laurie's site. Kind of the animals we see there. But it's very different than what we see in the Morrison. It's a very different assemblage of dinosaurs. And basically, I refer this as a Wealden-style dinosaur fauna. The Morrison, we have a Morrison-style fauna, which also occurs in Spain and Portugal. But the Wealden-style faunas are iguanodonts, polycanthine ankylosaurs, Maniraptorans, very different assemblage than what we see in the Morrison. And it's best developed, famous from the Isle of Wight, but it's also on the mainland and the Wealden Basin. But basically, these animals are found in sea cliffs on the Isle of Wight. I've been there. It's very much like looking at a Cedar Mountain, a yellow cat assemblage of dinosaurs. This Wealden style fauna. And this probably represents the last time when you could island hop back and forth across the North Atlantic, because we have animals in common. The Morrison, Portugal's loaded with the same genera that we have here. About a third of their genera in their upper Jurassic are the same as ours. But the thing is opening during this time. Always think of it like Indonesia. They're island hopping, but as it split apart, at one point finally it stopped. You couldn't cross the North Atlantic. That seems to happen at the end of this Wealden faunal interval before we hit the Aptian Albion stuff and the Ruby Ranch. This poison strip are our uppermost stuff, polycanthines. We have this new Utahraptor relative, just as big pretty much, but clearly not the same animal. We have a giant ankylosaur. We also have Gastonia laurimcwinii, Titanosauromorph sauropods, Veneniosaurus, and iguanodonts that are also known up in the Black Hills region. This is the one time slice we have in these rocks where there seems to be related animals elsewhere in North America. And this is in the Black Hills region, very poorly known fauna. It's mostly in forest, so it's not your favorite place to prospect. But we have Planocoxa. I think our giant ankylosaur is actually Hoplitosaurus and not laurimcwinii. But we see these last Archisternid iguanodonts and the last polycanthines in North America. So this is the end of the Wealden fauna. But this is if you saw Walking with Dinosaurs, Band of Brothers. This is the interval we were looking at for Band of Brothers in eastern Utah. So if we started looking, what's going on across this interval, the Jurassic-Cretaceous transition, everyone thinks Cretaceous having a big seaway. At the end of the Jurassic and the early part of the Cretaceous, there is no seaway at all. We do have a big river, the Buckhorn River system, that flows from down around Big Water up across diagonally through the swell and out around Dinosaur, Colorado, and then up into Wyoming, where it becomes basically the prior conglomerate from our Buckhorn. It used to be thought that that conglomerate came out of the mountains to the west. We now know it came from the south. And we can go to the east and west sides, as you'll see. But what happened to the, like Dinosaur National Monument, almost every animal there is gone once we get into the basal part of the Cretaceous. And we have that dated to pretty close to the base of the Cretaceous, way down the Berriasian, if not, possibly even at the top of the Jurassic. If we look at all the families of dinosaurs, and this is messy, we need more family trees, more phylogenetic studies. But there is a big transition among sauropods and the big meat-eating dinosaurs, clearly. North America loses stegosaurs. That doesn't happen on other continents. They survive into the Wealden interval. And then they go out. Looking at sauropods, see one of these papers came out just a few weeks ago, from the Brits. And if you look at that red line and all the things in red are North American stuff, you'll see we lose everything. And we have, where's this? I wish you could see this on here, but you can't. There's our Turriosaurs that occur in the basal Cretaceous. Here's all the Morrison dinosaurs, sauropods. Boom, gone. And here's Camarasaurs and things. Gone. Our Brachiosaur, gone. We lose everything. This is just the sauropod part of the story, but it's getting to be real robust. Chinese see the same thing. All the Chinese sauropods, Mamenchisaurs, Shunosaurs, and all those things, all gone at the end of the Jurassic, replaced by titanosauromorphs. So this is what we see in that transition. You have this incredibly diverse Morrison fauna. Almost everything goes out. We have a couple small theropods that probably give rise to a bunch of things like Utah raptor and the ornithomimids, and other things. But all the larger theropod lines all go out without replacement. Gone. We lose in North America, all the stegosaurs are gone. Of our ankylosaurs, we lose half of them. Gargoylosaurus is gone without a descendant. Mimorapelta might give rise to the poacanthines upsection. But those are ornithopods, the bipedal plant eaters, the hypsilophodont grade things, Dryosaurus, Camptosaurus. There's no sign that any of that stuff goes out. So it's a pretty biased turnover. Bipedal plant eaters seem to make it through in a big way. But we have people working on this in detail. But 10 million years of the Morrison fauna are followed almost immediately by 22 million years of a Wealden-style fauna. And when you look at this, get this thing back, Wealden, we have faunas that we can split apart, but they have all the same players. Related animals, there's turnover, there's evolution going on within those faunas. It's not all static, but it's the same cast of characters for a long time. And the Morrison, it's like at least 10 million years that we have a Morrison-style fauna around. The entire Kimmeridgian and Tithonian, maybe into the Oxfordian, so maybe more than 10 million years. And then, as I said, there's another extinction at the top of this interval. Another talk. But we have this Weissert signal plugged in real well. That's an international timeline. Find it in Japan, Europe, Southern Hemisphere. It's a period of time when the ocean systems went anoxic and gave us this really important carbon signal. But when you look at this chart, you see this big kick here, good marker bed, and it may tie to this faunal turnover, But then we get this kick here, OAE1A, tied to the Oncong Java event. That may be tied to this extinction event. We have another thing up here, OAE2, another major extinction boundary up here that's well defined. But if we look at the bottom, the Jurassic, we have really no evidence of much happening. So here's that bottom. This should have been earlier, this picture. But you see, here's the Paradox Basin. This is looking at just the ankylosaurs, polycanthines, and the raptors, the dromaeosaurs, just showing how rapidly they're evolving through this Wealden fauna. And we may have 6 to 7 discrete dinosaur faunas in this interval. The Morrison, the Kimmeridgian, most of it's one fauna. Salt wash may be another. There may be a salt wash fauna, a brushy fauna that are pretty similar to each other, but different. And then this uppermost one in Cimarron County, Oklahoma, the Denver Basin. But if you look at this lower, it's stacked fossil soils. And each one of these soils takes a appreciable amount of time to be deposited. You don't form a soil overnight. To get a well-developed soil takes time for the interactions between the atmosphere and the sediments to be working long enough to differentiate minerals and organic materials through that interface to give us a well-marked soil level. And if we look at this lower part, we see that there's a series of 3 soil types that we seem to trace through this whole region. And they're distinct types, and they occur in the same order wherever you have all 3 of them. Sometimes you're missing the lower one, without much question. So just to get across, Paleosols for dummies, I am not a Paleosol worker, but I hope someone's going to step up to the plate and do it. But basically, for me, if you got iron, manganese, and things, it's wet. You're leaching out all the salts, the carbonate, other salts out of the soils. So you don't get alkali. You don't get that crusty alkali coming up that we see out here every spring. If you get salts in the soil, even a little bit, these calcitic soils, it basically has to have net evaporation. So you saturate the upper parts of the soils with salts. So you get carbonate or sulfates. Our alkali out here is calcium sulfate for the most part. But you get these sulfate minerals or carbonates. But you get the salt, means it's fairly dry. Certainly under 25 inches of rain a year if it's seriously monsoonal or seasonal. In the lower stuff, we have, fossils down there. We've got dinosaur bones associated with these iron-rich soils. And then above them, we have these silicified, what we call histosols, or silicified peat beds, often called by rockhounds bacon agate. But these are basically agatized coal swamps, because it's so alkaline from the Morrison underneath it that basically it silicifies, just like wood would. And if it's pure plant material, it replaces like wood. And you can get microscopic detail, or it can be just banded agate. You get good preservation and bad. And that's how wood is. If you look at fossil wood. Here's the sequences in a few places. This is down by Blanding. This is the reference section of the Brushy Basin member of the Morrison, south end of Brushy Basin itself. And the bottom, bed 98, is pretty much pure kaolinite, porcelain clay, and quartz sand. And basically, the guys I'm working with on that did the clay chemistry on that, say that's an oxisol. That is a place where the rain this is in the top of the Morrison, where the rain on that erosion surface was so intense, it just leached it out. And theoretically, if we had aluminum-rich sediments there previously, we would get bauxite ore, because bauxite you get under these kind of conditions. But you got to have aluminum in a fair amount to get it to begin with. Above that, we get these iron-rich paleosols, and here we don't see the church so much, but I think we've got a few in this road cut down. Oops, I don't even have pictures of the other road cut. But this site, is a good boundary section. So kaolinite in the top of the Morrison, oxisol, and then we go up in these ferruginous type of soils. This is the I-70 road cut west of the rest area. Same sequence. You've got these white beds. Maybe they're kaolinite rich. We got to do more analysis. I'm not as happy with the data that I've seen. But above that, we have iron-rich paleosols, that rusty red. Then you start seeing the little chert layers, the histosols. And then we can see, go around the corner, that this goes right into that Buckhorn River system. It interfingers with the Buckhorn. And previously, these sequences over here on the other side of the swell were thought to be hills of the Morrison between channels of the the Buckhorn, and that it was wetter at the end of Brushy Deposition. But we can show that this interfingers into that river system really clearly. More work to do. Everything here needs much more testing. This is where we're mainly digging, the Yellow Cat area. Once again, in the lower part, we see these iron-rich soils, and then we get into these cherty beds, these histosols, and then further up, we get carbonate, the salts. Because the Morrison seems to have these calcitic, incipient soils, deposition rate's pretty high in it. Basically, I think we're returning to background. I used to think we were seeing the first evidence of the rain shadow, the severe, but I don't think that's true. I think we're actually going back to background climatic conditions. But this would have taken a couple million years. This wasn't like the next day that we have this, it gets really wet at the boundary, then slowly dries up as we go up section. That probably 1 or 2 million years. We don't have precise dating, but it wasn't a quick thing. It's not like an iridium layer, fallout layer. Here we are looking at it further to the west, and you can see this real iron-rich paleosol structure. This is over by Utah Raptor Ridge, by Don's Ridge. They actually mine manganese out of the Morrison Cedar Mountain contact. If you look at the old USGS bulletins, they describe these rocks as being in the Morrison. But that was before there was a Cedar Mountain formation, and the boundary used to be called a lot higher in the sequence. So it wasn't identified that these are at the boundary, these manganese mines. Here it is up north of Dinosaur National Monument, in the Rainbow Park area, and you see the same sequence. You get these Morrison beds with incipient calcisols, an interval of wet and white rock, very ferruginous, very gravelly, and then we eventually get back into carbonate, so you get the rebound. But that whole sequence here, from here to here, probably took a couple million years, or at least 1 million years. So it's, a long-term recovery. And we got fossils in the ferruginous ironstones. So a lot more work to be done with those. Why does this happen? One thing we have at this time is the Maraquigan crater in northern South Africa. It's about 80 kilometers, 70 kilometers across. It's a pretty serious impact structure, but it landed on the craton, on crystalline continental rocks. Just not in the ocean, not on the edge of the ocean, right on the old crust of the earth. The crystalline cratonic rocks. Did it do it? I mean, they drilled this thing quite a bit. They actually came up with half-meter-sized chunks of the asteroid. So it's all in there still when they core it. But is that the one that did it? Well, there's a similar crater, which I love how it is. The Manicouagan crater up in Quebec also hits cratonic rocks up on the Canadian Shield, and it's tied to the Revoltian Adamanian faunal change in the Chinle Formation. It's very well documented. And it's actually tied to a cherty histosol bed in the petrified forest with silicified roots and everything we see in the Yellow Cat, which is really interesting. But you see the faunal change there, all different species, and we lose, therapsids, dinocephalians, but it's not a giant extinction, no more than we see within the Yellow Cat or within the Morrison. So I just don't think that's that big a deal. But it's, so the one in South Africa might not be that big a thing. But Shanxi Rise is another thing. This also is at the Jurassic-Cretaceous boundary. A good buddy of mine, Mark Leckie, used to be the chair of UMass geology department. He was on the leg that drilled this thing 7 times. And they interpret it because of seismic stuff they did there. They parked the ship on it for a long time. It's the largest shield volcano in the solar system. It's bigger than Olympus Mons. The Tamu Massif, which is this lower part here, is that shield volcano. And the whole thing is big across as the Japanese archipelago. It's a big deal. It's a very big feature. And seismically, they can see a structure like a shield volcano. And they interpret it generally as maybe a failed triple junction, the continent, the oceanic crust trying to split apart. I think it's just as likely an asteroid impact plowed through the oceanic crust, exposing the mantle, because oceanic crust is real thin. And you expose the mantle, you're going to end up with a huge volcanic center. And this would have taken millions of years. So see this thing where it's like it's a millions of years thing happening. This makes a lot more sense than a bam impact, doing it. Because this would have been happening, and as it waned off, climate would have changed. This would have put tons of water into the atmosphere, greenhouse gas, would have changed the Earth's albedo, cloud cover, would have caused a lot of rainfall. Remember, it's really wet across that boundary. I think it's a really good candidate, as do a number of my colleagues that don't like the asteroid part of my story. But that's, just a hypothesis. Oops. There should have been, oops, dang it, previous. Yeah, this slide. No, it isn't. Where is the slide? It must be later. But anyway, then, this newly identified voice carbon excursion. Remember I said there was nothing going on at the end of the Jurassic? I heard about this a month ago for the first time at this conference in Germany. There were several lectures about it. And it's this big excursion at the end of the Jurassic. I was communicating with the chief paleontologist for the Canadian Geologic Survey. She's published on this. She does microfossils, and basically she's on the committee to establish where we're going to put the JK boundary. Because that's the one big boundary that they haven't put a golden spike in yet. It varies by millions of years, depending on who you talk to. French want it high, the Canadians want it lower. But she'd like to move it down into the mid-Tithonian and tie it to this thing, since this should be also a global signal. In a lot of places, it's a gap, so they don't have it preserved. But it should be a global signal. And I wonder, is it tied to the Shanxi rise? These are all things, they're going to debate this in a decade. I'll be dead and gone. And a lot of this stuff is still going to be areas of major debate, among scientists. There's still debate at the end of the Cretaceous. I just want to point out, Ontong Java, which is the Aptian, event in Indonesia, has been proposed to be an asteroid impact. It's another submarine impact, big giant flood basalt sequence. And so when I saw this paper, I said, Shanxi could do this, it could be the same thing. But I guarantee this is being argued widely. But if you look at seamounts, the Pacific plate was moving this way, hot spots, in what single, staying where they were. So you got a chain of these seamounts that go from the northwest to the southeast. Shanxi rise, if you look at the scatter of these massifs, they're almost 90 degrees off. And then if you line that back across to South Africa, it could all be part of the same event in my mind. Once again, people can work on this. It's not going to be, no one's going to believe me. That's why I try to work with people who know more than I do, because they make me look good. But basically, was the Cretaceous sandwiched by asteroid impacts? It's conceivable. But clearly, there's a big event here, certainly a big event here. This rate in here, extinction event, that's when we open up the Alaskan land bridge, immigration-induced extinction. Big event here, major extinction. We have these various events, and they generally have global records. This is all stuff that work will continue, and there'll be additional data substantiating it or knocking it down. That's how science works. Your job, you choose to take it, is to prove I'm an idiot. That's how science works. You put it up, and then it's up to the next generation to test what you're saying and see if it holds water. And that's, basically what I'm throwing out here. I'm 72, no more 10, 20-year projects. This was a 35-year project. That's funny. It's not even going to the last slide. Well, the last slide was the last slide. So it's just acknowledgments and all of that, which I don't understand why it didn't go to the last slide, but it's not really needed. But basically, we have this incredible record. You know, this is stuff that can only be examined properly in Utah. You know, so hopefully it'll encourage more scientists around the world to come here and work with us. You know, the only way you solve these mega problems is by collaboration. And, you know, collaboration with researchers throughout this region and the world is critical. And, you know, we'll just keep learning more about this, and who knows how this stuff may eventually stabilize. But something happened at the end of the Jurassic. I will put my sword into that thing, and, you know, no one's going to stop that. That's true. But what? You know, now, you know, we start the debate. Any questions?